So, just a moment here. Right. So as I understand it, there's going to be a talk by Nikolai Rusik 1 hour after mine, right? When does his talk start?
It will start on in 2 hours. So it will
In
be
2 hours.
right.
So okay, so that means it will start at 11 o'clock my time.
Right, right.
We will talk for about an hour and a half now.
Yes, and then half an hour break or
Okay. So so I want to talk a little bit about rectangular diagrams in relation to Nikolai's talk, which is about training a computer to handle these diagrams and to do not theorize machine learning. But the rectangular diagrams, which are championed by Igor Dimitrov, are a very useful kind of diagram for knots. And some of you may not have seen these diagrams. Let me explain how they work. So if you drew a knot diagram, I'm not putting over or under crossings here, by drawing either horizontally or vertically like this until you were done and came back to where you started, that would be an arc, sometimes called an arc diagram or a rectangular diagram. And the convention is that whenever you see this, it means this, that the vertical line goes over the horizontal line. So that means that a flat diagram represents a classical knot. It represents a unique classical knot. In this case, we can see what classical knot this represents by putting in the crossings. So let's take a look at that. So let's see, do we have a knot or not? Something simplifies, right? This diagram is equivalent to and I can stay in category, as you see. There's a Reidemeister 2 kind of move. I can just pull this one in. I'm staying in the category of these rectangular diagrams when I do that. I end up here. Let's see, what else can we do? You can see that if I were to go out of the category of these rectangular diagrams and just look at it as a knot diagram, then your intuition will tell you what to do about it. Let's look at that for a moment. That's the same diagram written as an ordinary diagram, right? And then you see, oh yes, I can twist this under, um, and this one under, and I will end up replacing it by excuse me. Let me do it by erasure. So I want to throw this over and bring this under. So that means that I'm going to, oh, something there. This switch goes over, could go over here. There we go. Like that. Now, what do we have? Over, under, over, under, over, under. It is definitely alternating, and so it's reduced. We could simplify it a little bit more if we wanted to. We could go from here to here. And you see it's Treffa. So, the question is, what about staying in category? I went out of category. I stopped worrying about it being a rectangular diagram. I want to see whether there are other moves that could be done on this diagram as it stands. And so let's look at this a little more closely. I want moves that would be in category. Um, let me just move this a little bit. That certainly isn't going to take it out of category. I'm just making something available to myself. I just push that rectangle that way. And then you see that this could be moved down. You see this L shape? This arc here can be moved upward, or that one could be moved downward. That would be all right. It preserves the structure. So in other words, I could, if I want to, replace the horizontal arc you see by a horizontal arc just going like this, right? I'm going to move this arc. This horizontal arc is in between the endpoints of this, or in between the endpoints of that one. So this is entirely underneath, and it can be shifted up across a rectangle underneath to here. And then we can remove this. So we begin to discover moves that are in the category of the rectangular diagrams that can be made. And then we see, yeah, I should have some corner moves. I should be allowed some corner moves that would remove a thing like that. And if I'm allowed a corner move, that will, of course, keep me in the category, and I will get down to something like this. And indeed, as you see, now by staying in the category, I have gotten down to trefoil knot also. So the upshot of this is that there exist moves in the category of rectangular diagrams. And those moves consist of, some of them are like this. They would be simplifying or complexifying moves like that, corner moves. And there are other little corner moves that you can articulate like this. Yeah. The stay in the category, things like that. Then there are also basically, other kind of move is basically this kind of move. Maybe you have this, and maybe you have this in between, like that, and then you could exchange that um, for somebody like this. And I don't bother to draw under and over because this goes over. Yeah. And there could be other things in between as well. Maybe you have some lines in here or vertical lines, but they are also over. And so all of this works just fine. That thing that moved was under everything. Um, and then, so these are exchange moves. And then there are another set of moves which have to do with exchanging across the whole diagram. So, for example, here, if you look at this arc here, you could take what's here, which goes under, and goes entirely under, and you could swing it. Maybe I'll illustrate it for you. All right, so now let me use another color here. So what I have in mind is I'm thinking of pivoting on the vertical line here. No, I'm sorry. Pivoting from here to here. There's this horizontal structure is entirely underneath. And I can swing it all the way over to the left. So then it would be over here and over here and over here and over here. You see? And I could just swing it like that all the way across on the outside like that. And that's an external swing move. Maybe Dinikov calls it something else. I've forgotten what he calls it. But you see that's a useful move to have, and in fact you need to be able to do that sometimes. Notice that, very interesting, right? When we did that eternal swing move, we went right directly over to the trefoil knot. So there's a very intelligent set of moves that you can basically find just by saying, I wish to remain in category and make moves on these diagrams. And then there is a notion of complexity of diagram. And the complexity of diagram is the number of vertical arcs. You see, a diagram has a number of vertical arcs. 1, 2, 3. These are distinct arcs. They should be 4 and 5. Just shift them a little bit side to side. These I drew it in an uncanonical way. But this one, 1, 2, 3, 4. Again, to illustrate one with a canonical set of vertical arcs, I will just push this a little bit to the left. 5, 6. 1, 2, 3, 4, 5, 6. So we'll call the complexity of the diagram equal to the number of vertical arcs. And of course, that equals the number of horizontal arcs. And then what Dinikov proves is that if D is unknotted, then there exists a sequence of moves. We'll call them D moves, Dinikov moves, the ones I've been discussing here. Sequence Dinocoff moves, taking D to the unknown, that do not increase complexity. This is a great theorem. This is for the first a simple, direct, diagrammatic, combinatorial algorithm that will unknot a knot if it's unknotted. So if a knot is unknotted, it can be found out by a finite search, because as long as you don't increase the complexity, you're actually working, and I'll answer you of that, I hope, in the next slide. Okay, you're actually searching a finite space, a large finite space in general, but it's finite, and so all you have to do is look and until you find moves, and it will go away if it's unknotted. That's the theorem. So Nikolai Nikolai Rusik and Iskander Timonov and myself have been working on a paper about using the computer to work with the Dinocoff moves. And the first part of the research, which is what I will tell you about, is about using the Dinocoff moves to create a lot of unknots and then and other knots, and then have the computer use basically pattern recognition to try to recognize when things are knotted or unknotted. Another part of the project, which I hope we will eventually do, is to have the machine learn to do these moves in an orchestrated way, like playing a game, and become very good at unknotting. But let me say a few more words about this, and I'll give you a demonstration about it. Okay. Let's just familiarize ourselves with these diagrams a little more. Suppose that I draw a diagram. Oh, I don't like that diagram. I want my columns on different verticals, right? I told you I did, and I do. So let's conform to that. Good enough. We'll take that. But it's a matter that I want to show you now. If I make horizontal lines through all of the... Oh, let me see. Just before I do that, I want to know where the diagram's corners are very clearly, because otherwise I may draw over them and be unable to know what's going on. And now I want to draw some vertical and horizontal lines, and I'll make them a little bit slimmer. For every horizontal arc, I'm going to draw a horizontal line. Too close, but it's all right. And for every vertical arc, I'm going to draw a vertical line. And now you see that our knot is lying on a grid. All right? It's lying on a grid grid, which is 1, 2, 3, 4, 5 by 5 in this case. And our curve is drawn on as a subset arcs of this grid. And so another way of thinking about what these are is that they are drawings of knots on a certain size grid. And that's why now you can see why I say that now, so the complexity here equals 5. And when I said that you could move an unknot around, keeping its complexity no greater than 5 if it was by 5 grid, it means that you are restricted to working on the 5 by 5 grid. There are only finite many things that can happen. And so you're searching in a finite space to get it to be unknotted. Now, this isn't the greatest picture I ever drew, so I'm going to remove it, and I'm going to draw a simpler one and do another example. Let's take a trefoil to begin with. Because I want you to see how we can code these, and it's a different thing than the Gauss code, but a very effective code. So let me draw the grid. All right, now I'm going to do something else, which is quite nice. I'm going to walk along the knot, and I'm going to alternately write white and black markers here. So in order to do that, I'm going to make big black markers to begin with, and then I will make some of them white as I go along with my eraser. And you'll see why I do this in a moment. But the amazing thing about this diagrammatic is that it's corners that determine everything once we have it on a grid. You see, because once the corners are there and you know the sequence, then you know the whole thing, including the crossings, but you don't have to tell about the crossings. And once you have a crossing, the weaving of it is over vertical. So now here we go. Black, white, black, white, black, white, black, white, black. Now you know that black is connected to white, and white is always connected to black. So if you know the white ones and the black ones, you can forget about the curves, the connections, because you know what to do. Just imagine that you can't see the knot. You know that it goes from black and alternately horizontal and vertical, black to white, white to black, black to white, white to black. And so there's the knot, reconstructed from the set of white nodes and the set of black nodes. Now, for coding, label the arcs 1, 2, 3, 4, and 5 horizontal arcs, and 1, 2, 3, 4, and 5 the vertical arcs. And then you see that there is a black permutation, and there is a white permutation. Excuse me. Yeah. Just getting myself a little room here. All right. Now the black permutation. Row 1, row 2, row 3, row 4, row 5. And what do I see? I walk from row 1 and I see it 2, goes to 2. Row 2, 3. Row 3, 4. Row 4, 5. And row 5, 1. The white permutation. Row 1, 5. Row 2, 3. Row 3, 4. Row 4, 5. And row 5, 4. I'm sorry, I got myself confused. 1 to 5, 2 to. Oh yeah, I flipped from black to white, didn't I? I'm sorry. I was doing the white permutation. So 1 to 5, 2 with 2 to 1, 3 to 2, 4 to 3, and 5 to 4. So this pair of permutations encodes the knot. Isn't that a cool coding? So that's the way we tell the computer what the knot is, by that coding. And also, you may be interested in learning about a subject which is outside the range of our course unless we add more time, but there's a subject called knot floor homology, which is based combinatorially on the rectangular diagrams. There are a number of different formulations of the knot floor homology due to I'll misspell Oszvath, Osvath, and Zavo. And you will probably have heard of this, but this theory has a very interesting complexities at many levels. There is a combinatorial definition of the homology by using the grid diagram or arc diagram, the Unicroft diagram method of representing the knots. And then the proof that it's invariant goes down to the D move and so on. So this is a very interesting of coding knots. And there's a computer program that exists which lets one play with this, and I want to show you that computer program. So here it is. This is GridLink, produced by let me give you a reference. Written in Python by Mark Culler. At University of Illinois, Chicago. And you can find it by looking for his web pages. But a copy for Mac anyway, Mac computer, will be in our Dropbox. In case you want to play with it. I'm going to play with it for a few minutes now so you see what it's like to play with the program. So let me it will take as inputs the pair of permutations and all that. I'm not going to bother you with it now. Maybe next time, after I've refamiliarized myself with the program, I'll do a few more things with it. But for right now, I'll just use some files that I already have. Here's an unknot. So let me show you with the program now. Maybe we can make this a little larger so you can see better. I'm not sure how that works. Yeah, a little larger. All right. So when you bring your mouse over to the diagram, it shows you things that can be exchanged by a move. You see the two blue lines? One of them has its endpoints inside the other, and therefore we can do that. Notice also that it illustrates the crossings, even though it doesn't have to. Here's another pair. Here's another pair. Let's see, what else can we do? I want to do something. Here's an outer exchange. You see those two? When I click them, it'll swing around. These can be exchanged, but that's not so interesting. These two can be exchanged. Let's see. These two can be exchanged. Then these two can be exchanged. Then these two can. Whoop, that's not the way I wanted to go. And these two can be exchanged. And now I'm unknotted at least, and I'm going to have to choose the right moves to make it turn into a rectangle. But I got it unknotted. You see? So that's how it goes. Now you could take a more complicated example if you've produced one, like let me see. One that I call the culprit. Let's get rid of that. This one is unknotted, but it'll take some cleverness perhaps to unknot it. You can ask the program to go ahead and unknot it. You say simplify. And it did it. But of course, it doesn't show moves. Now, it may be that you can actually review the moves. I'm not sure. I have to look at the program again. I always forget what's available in a program. Yeah. So, so you can try it out on knots and on knots. Let's see. Let's look at an input file just to see. You see, these are X's and O's, for example. It'll show you that. It'll show you a grid. So, would be more interesting to open a file and then do that. You know, forget about that. This is actually an interesting example. You're looking for moves that you can do, and you find out that the only moves that you've got available are these external exchanges. So this actually is unknotted, but you're not going to unknot it except by an external exchange move because there isn't anything else available. So then you try, we'll do an external exchange. Let's see, now what can we do? We could do another external exchange. Now we get a simplification. We could simplify there. We can do that. We can do that. Could do that, but that's not so interesting. So you get a picture, and maybe you got frustrated or tired of doing it by hand. You say, all right, let's simplify. Turns out it's not it. So you can play the game of getting used to the moves and doing them by working on this program. Nice program. And the program also calculates Haggard floor knot homology for these diagrams by using the algorithm that's associated with the grid link diagrams. Maybe we could see what a calculus looks like if I have a file that's actually knotted. Otherwise, I'll have to draw one. Figure 8 knot. All right. So is this truly a figure 8 knot? I don't know. Let's ask it to simplify it and see what it gets. Yeah, it turned out that it was simplifiable. So again, you could play the game of trying to simplify. By the way, there isn't a canonical way to simplify any knot. If there were, then the Dinakoff moves and the arc diagrams, the rectangular diagrams, would completely solve knot theory, but it isn't that simple. Then we could ask for the invariance. And you see, there you go. It's telling you, it's giving you the exo diagram. There's the permutations for this guy, and here's the matrix of ranks of the homology groups in this theory. So this is a very nice, concise program that can give you an introduction to a lot of these matters. All right. Well, that's my introduction to the grid link the Dinakoff rectangular diagrams. Any questions before we go on to something else? Okay. One of the things that I was impressed by a bit about these diagrams is how natural the moves are once you say the diagram knots this way. And a nice exercise for you is to prove, easy exercise, is to prove that any knot can be diagrammed this way. Let's write a couple of questions. Any tame knot diagram can be put in rectangular form. Exercise for you. Okay. Second question. How would you do a theory of virtual rectangular diagrams? Now, part of the answer seems obvious in a way, right? You could say, oh, well, here's my favorite virtual trefoil. Right? There's our virtual trefoil. No complaints about that, right? There it is. So we have a rectangular diagram. Indeed, it's true. You can have a rectangular diagram for virtual knots. But then the next question, so diagrams work. But not determined by black-white, right? Here, I could do the black-white. I could color these vertices. And I could go into my black-white phase, black, white, black, white. Well, I have to make it black before it becomes white in my method. Oh, you don't mind. Black, white, black, white, black, white, black, white, black, white. All right, but then you see, nobody told you about the virtual crossing. How do you know? You have to just have it there, along with the black, white. So, so you didn't just give it in terms of the white permutation and the black permutation, some extra information having to do with the virtual crossings. And so, uh, and so this is an interesting question about code. Maybe you'll think of a nice way to code and moves, right? It would be interesting to have a good formulation of that. This, instead of being an exercise, is of course a research question. So that's the story. Of course, you could say, well, what we could say this way, we could say, well, we have grids. And on these grids, there is some extra structure. And there will be some crossings in the grid that are designated as virtual. And then if you use them, then you will find yourself a virtual knot. So you would have a grid with virtual crossings, and you would have the two permutations. That certainly does code it, but I don't know. I don't know what's the best thing to do here. It's a nice question. So that's where I'll stop with this part of the talk about the Diener-Krupp diagrams. But remember, the key theorem about them is that you can actually search them and find out whether something is unknotted. And that's how Mark Color's program works. It just randomly searches for move, just like it shows you what moves are available to them. And of course, it isn't making it more complicated. So after a while, it finds a pathway down if it's unknotted by Diener-Krupp's theorem. So I found that really amazing and inspiring that it's actually possible to figure the unknotting of a knot if it's unknotted by something that's purely combinatorial. Okay, so now let's go back to what we were talking about before, if I still have it up. Yes. I'm going to use a slideshow and take a look at some other examples that we hadn't talked about. And since this slideshow does some things that we haven't talked about at all, I won't talk about them today. I'm going to let go of talking about covariant homology at this point, but we will talk about it, and for virtuals, maybe in the lecture, but let me just skip that for now. I'll get you the slideshow, though, in the Dropbox, so you can look at this for next time. I will talk about the covariant homology next time, but we're skipping that. This is the fastest lecture you ever took on covariant homology, right? Yeah. Then we get to virtual knot cobordism. And now I remind you of a couple of things about virtual knot theory, and then we'll get into talking about cobordism. So these are the pictures that we're well familiar with, right? That if you have a virtual diagram, then you can form a ribbon graph associated with it, which is a bit of surface with boundary that hugs the diagram. And the virtual crossing becomes a disjoint pair of ribbons that carry one arc and the other arc. And then when you project this down into the plane, you get the virtual diagram. The projection of the joint arcs becomes the virtual crossing. On the other hand, we do not think of this as embedded in three-dimensional space. We just are using that as a crutch drawing. It's an abstract surface. And by the same token, you can go backwards. You can start with a nut in a surface, form the neighborhood, extract it, and project it. And by the way, we can figure out the genus. This is something we didn't do when we were talking about it before. I'm walking through the slideshow and picking up bits of things that are useful to us. See, here's the ribbon construction for this virtual crossing, virtual diagram. And then we're going to build a surface by adding adding cells to the boundary components. And that means that we have embedded in this graph cellularly a graph with two nodes, two vertices, this edge, this edge, this edge, and this edge. That makes 4 edges. So the number of edges is 4. And we don't need to worry about the number of edges anyway because it's a 4-valent graph. So 4 times the number of vertices counts the edges twice. So that says that the number of edges is 2v. And maybe I should do this little extra on my pad. Let me do it on my pad. The point is that if you have a virtual diagram, we're just talking about this as a graph, then you see that you have vertices is equal to 2. 4 times vertices is twice the number of edges. So in this case, twice the number of vertices is equal to the number of edges. And in this case, you see the number of edges is equal to 4. And there are 1, 2, 3, 4. So an edge is a traverse from one vertex to another, doesn't keep track of the virtual crossing. It's the abstract graph we're talking about. Then, with regard to that, we are building this ribbon surface. And we build the ribbon surface by doing this construction. At a virtual cross, goes straight through and forms a bit of ribbon like that. And then we add disks to the boundary. Now, how many boundaries do we have? Here's one boundary, and here's the other boundary, right? It's one single boundary, right? So lambda equals number of boundary components and that's equal to 2 here. So we have vertices is 2, edges is 4. Then we get a surface. you start with the diagram, and you get the surface of the diagram. Surface of the diagram is obtained by adding disks to the body of the ribbon. Okay, now we have to know that for a surface, the vertices minus the edges plus the faces. This means nodes, edges, and disks. The number of disks that I added in is going to be equal to 2 minus 2g, where g is equal to the genus of the surface. This is the generalized Euler formula. You may be familiar with the special case of in plane 2, but for surface 2 minus 2g. Well, let me give you an example of that, and I won't prove it. I'm going to leave it to you to look it up elsewhere if you wish. But here is a simple example. In this case, we have vertices equals 1, edges equals 2, this edge and this edge, torus, right? And then face equals 1, and notice that the interior of the face is a disk. That's because what we're looking at is the identification space for the torus. A, B, B, right? And this thing in here, that's the disk. Now, when the disk got mapped down into the surface, got some identifications made on it. But what we need is that the interiors of the add-ons are disks. And they are if you form a little ribbon neighborhood of this. So what do we have? We have here in this example, we have vertices minus edges plus faces is equal to 1 minus 2 plus 1, which is 0. And 2 minus 2g is equal to 2 minus 2, which is 0. Check, right? Genus is equal to 0. I'm sorry, genus is equal to 1. 2 minus 2 is 0, is to 0, right? So that's an example of the theorem. And that's what's happening here as well. Let's see now, we can derive a general formula because V is the number of crossings in the knot. E, we just figured out, is 2V. And F, the number of disks, is the number of boundary components, lambda. And that's equal to 2 minus G. So I have that minus V plus lambda equals 2 minus 2G. Or maybe better, 2G minus 2 equals V minus lambda. Or G, therefore, is equal to 1 plus V minus lambda divided by 2. So this allows me, if I have a virtual diagram, let's do an example. Just useful to have this around. So we just worked out that the genus is equal to 1 plus v minus lambda divided by 2, okay? So take any example you care to play with. All right? And we want to know when we fit this onto a surface, this diagram, what will the genus be? So we just go ahead and do our work. Right. See, I don't know how to find the number of boundary components without doing a tracing, but that's all right. That's not so bad. I just do the tracing and find out in the end how many boundary components I have. Let's see, that's connected up there. This goes here. There's my ribbon surface, right? If I want to pretty it up, I can make these ramps look a little better. It will look better that way. Yep. Now, one node, two nodes, three nodes, four nodes, five nodes. So V is equal to 5. Now what about lambda? Well, I'll mark that one and take a walk. Wow. Did I traverse that? I think I did. Let me just... Yeah, I did, didn't I? Everybody got traversed, right? So lambda is 1, and the genus is equal to 1 plus v minus 5 minus 1 over 2, which is equal to 1 plus 2, which genus is equal to 3. So that means when you take this surface and you fit the disks on it, just one disk, you're in a genus 3 surface. And that's where that virtual knot would sit. And that will be this genus for a given diagram. For the diagram, but not necessarily for the... What is the issue here? Important to see this issue. Let's go back to a simple example. Suppose that I did the construction for this. Now you know the equivalent to this, which is equivalent, so it's really in genus 0. But as far as our construction for this diagram, it goes like this. And so it ends up on a torus. In fact, you could draw it on a torus like we did before. You have a torus. And on the torus, there is this guy here. And he's wrapping around like that. And if this crossing weren't trivial, you see there's a 2 move. So after the 2 move, this comes not really living on the torus. And so while it is placed on genus 1, it doesn't have to be on genus 1 because after you do the move, it lives on genus 0. And if you were to look at it on the torus itself, you would see that it could be simplified on the torus. So if we looked at it just on the torus, then we would see that it was equivalent to this. And then you will find that you can steer this away and make something simpler. For example, one way to understand that is you can just form a neighborhood in here. After you do the move, you can form this neighborhood like that. And that neighborhood is just going to be an annulus. It's not going to be a torus. And then when you add disks to the annulus, you're back in the plane. So, this surface, this diagram is equivalent to a simpler diagram lower genus. So that's part of the story about genus. To find the least genus on which the virtual knot will live is a relatively complicated problem. But to find the least genus on which the diagram will live, that's given by our construction. Let's go back to the slideshow now. This is what I said to you off the slideshow, and there it is in the slideshow, so we can figure out the genus. And then we studied this knot, and we showed that it had trivial Jones polynomial, and we also calculated that its index polynomial, its affine index polynomial, was non-trivial. We'll come to that. And we talked about handle detours, and of course we talked about these moves. And then there are some variations of virtual knot theory that I'm not going to worry you about, but we have the bracket polynomial. And you can do calculations. Like here's a nice encapsulation of the calculation of the bracket for the 2 crossing non-trivial virtual here. And then, as we've said, if you note that the bracket is invariant under this replacement, then we can make infinitely examples of knots that have trivial normalized bracket. And we went through doing this. And then the switch picture is worth remembering as well, that if you do this virtualization, which means that instead of coming down through, you come down through virtually, then up through, and then back down through. And then it has the same bracket polynomial as this, but this is the same as the switch of that crossing. And we talked about that. And we also talked about the odd rod. So I'm reminding you of some things. But now we get to something new for our last half hour. I want to talk about cobordism of virtual knots. And cobordism of virtual knots is about the following idea. I could introduce it this way, and then we'll talk about it more than one way. That I am going to allow a diagram to change in this way. You have arcs in the diagram near one another, oppositely oriented, like that. And then if you thought of a surface, you could go through a surface and end up with a diagram that has this kind of arc configuration locally. And you would have two knots and time between them, force space between them, so that one knot was in the upper part of the time, the other was in the lower part of time space, and there's a surface between them whose boundary consists of the upper knot and the lower knot. It's a cobordism. The generators of cobordisms consist in going through saddles or letting a circle die, that creates a bit of surface, or if it's unknotted, or letting it unborn, that's also available, creates a bit of surface. And then you see some different examples of cobordisms here. So the main point is that we're going to add to the Reidemeister moves for free cobordism, allowing it to go through saddle points and allowing some deaths. But then we're going to think about the surface that's generated. And sometimes when you generate a surface, you don't generate any genus like this. But sometimes when you generate a surface, you generate some genus. Like if you go through a saddle point and then you go through another saddle point, you may generate genus in the surface. So this is a topic which is a very interesting topic in classical knot theory, and I'm showing you how it can work in knot theory. Before I go further with this in the slideshow, I'm going to talk about it, classical knot theory, a little bit so you get a feel for it. So I say that a classical knot is slice if it bounds a disk in force space. And by force space, I mean the following. Here's the three sphere, and here's your knot. And here's the disk. And here's the knot. And this is force space. The four ball whose boundary is 3. Okay? And that's the four-dimensional foray we're going to think about. So let's look at an example. It's a trefoil knot. Here's the mirror image of a trefoil knot. I'm going to take their connected. So this is trefoil connected some mirror image trefoil. And now I want you to note something about the orientation here. You see that, right? But this goes up and this goes down, so that's a candidate for going through a saddle point. So let's go saddle point. Now, I may have made my life a little bit crowded, but not too bad. I'm going to bring those two arcs together. All right, now that's this way. Oh, I'm going this way. And this one's going that way. This is going down, that's going up. Right. Now I'm in a position to get them. I'm not happy with the space I'm making on my blackboard. Let's move things around a little bit. Better. Right. Cut off a little bit. Okay. So now I'm going to go through the saddle point. So that means that we go from here to here. All right? Saddle point means here you see this, and here you see this. Right? And all together, that is a bit of surface, an orientable bit of surface from one to the other. Like, okay? It's worth your while to make things of your own to see how this stuff works. But now, let's use another color in here so we can see what happened to the two components that appeared. Let me just trace this one in black. Do you see it? It's unlinked, right? At the next stage, we can do it in a stage or two just so it's completely clear. Do a Rademacher 2 move right there. Simplified it considerably, and then I pull on it a little farther, and after a little while I have a red curve over here and a black curve over here, disjoint from it by moving it along in time, and then I let these get capped by dying, right? And what I then have is the following. I started with the knot, went through a saddle, and then I let these two die out. One black and the other's red in my picture. So I'll draw that like that. Yeah? And that's what happened. That's the story. So that says that this bounds a disk in D4, in 4 space. This is not special for T connected T star. It's true if you take any knot, take its connected sum with its mirror image, then all this same kind of thing will happen. There's actually another reason for this, a more geometrical, direct one. Maybe you'd like to think about it. The more direct geometrical one says, think of this as a string which goes around like that and it's anchored here. Rotate the string upward in 4 space until it comes back down, and it will come back down turned into image, and it will have traced the disk as it goes up and back down. I'll just say it that way and you can think about it. Geometrical, but it requires a little more care in formulating the 4 space. Here, see that we can just go through saddle points and we can make a knot and our image cancel each other out. This means that there are inverses to knots under connected sum from the point of view of this way of thinking, which is not true in general. You can't add 2 knots in 3 space and get them to cancel. They're non-trivial. So that's the beginnings of the subject of narrow-boardism, but I need a little more about the formulation of this. So you can think of a 3-sphere here and another 3-sphere here, and in between you have S3 cross the unit interval, and that of course is sitting in the D4. Right, it's just this stuff. And suppose that you have a knot in here, and you have another knot down in here, and maybe you have some surface which goes from one to the other. Surface S, which starts in a knot K and ends in a knot K prime. And S is a surface which is embedded in S3 cross I, with the boundary of S is equal to K in union K prime, where this K is in S3 cross 0, and this K prime is in S3 cross 1. So we'll assume that S is an orientable surface. If the genus of S0, we say that S is a concordance between K and K prime, or we say that K and K prime are concordant. So this is the generalization of isotopy, because if they were isotopic, then this would just look like a simple tube. But the kind of tube that I've illustrated, the more general concordance tube, could be much more complicated. It could have a lot of wiggling in it like this, and does that mean? It means that as you went along, somebody got born, interacted with you, somebody else died off, and you had births, deaths, and saddles, but it all added up to genus zero. It didn't have to. This is a concordance. Something like this is not a concordance. In this case, we created genus in the middle. We went through two saddle points, went into two components. They went through a saddle point back to one. Not a concordance. So then I was talking about slice, and I need you to see what slice has to do with concordance. Suppose you have a slice knot. Well, then all you have to do is take out a little ball around some bit of it over here like that. So this is another S3, and this is a trivial knot. This is a disk. And you see that K slice implies that K is concordant to the unknot. If and only if. They mean the same thing. If you have a slice knot, then it will be concordant to the unknot by finding a little ball and taking it out around a minimum there. On the other hand, if it was concordant to the unknot, why, then you can cap off that unknot and you will be done. You will have a disk whose boundary is that. So slice knot and concordant to the unknot mean the same thing. Now, it is a fact that K connected sum K star is concordant. Is concordant to the unknot for any classical knot K. And if K is concordant to K prime and L is concordant to L prime, then K connected sum L is concordant to K prime connected sum L prime. And so the upshot of all this is that concordance classes of knots form a group. And the inverse is the mirror image. So that's very pretty. And one would like to know, what is the concordance group of classical knots in the three-sphere? And this is not fully known yet because there are complexities. You might wonder, for example, does anybody else slice other than a connected sum or mirror image? I'll show you. and then we'll talk a little about virtuals, but we're running out of time. It's good that you get a classical picture of this question. So I want to show you an interesting example due to Ralph Fox a long time ago, I believe. So let's call this knot K, and it's ripe for doing a saddle point right there, yeah? So let's see what happens if we do a saddle point. Now we need to see the components that we got again, like we did in the case of the trefoil knot. So let me thicken that a little bit and take it in red and trace a component. Okay? It's unlinked. Right? Pull this around and take it off. So that means that at the next stage we can have an unlink and an unknot, and then we can cap it off, and we can cap it off, and I have my time going this way into the interior of the disk, and so K is twice. And K is not equivalent to a connected sum of anybody, not a connected sum, much less with a mirror image. You have to prove that by using the Alexander polynomial, or you can even use the Jones polynomial to prove that. So that shows that the phenomenon of being sliced, when are not sliced, that's the question really for determining cobordism group, concordance group. When are not sliced? Exactly when? Tell me when a knot is sliced. Very hard. You can make a lot of examples. You see, you could, for example, take two curves like this, wrap one around another quite a number of times, and then go through a saddle to get one curve, and you would have a knot that was sliced. You can make a lot of examples, but if you give me just the knot that you produced, it's going to be hard for me to tell what you did. Where's that saddle point? So this is a tough problem, and I'm interested in generalizing this tough problem about classical knots to virtual knots. So let me just show you a little thing, and then we'll. Where's the slideshow? There it is. Here is. This knot here. This happens to be called the stevedore knot. At least that's what Fox called it. I should look in a book on practical knotting and see if there is a practical knot called the stevedores knot that corresponds to this. Maybe you should look that up next week. But here is the virtual stevedore. Now, what I've done here is I've virtualized this crossing virtual and that virtual. I'm going through a saddle point similarly, but I use a virtual curl to go through this point. And now take a look at what we have, and you see that we have 1, 2, 3 fold detour, right? So this is all virtual and can be flipped in, and then it's unknotted, unlinked. And so it's an example of a slice knot in the virtual category. And we can show that this is something that's happening strictly in the virtual category, not really in the classical category at all. Stevedore is not a classical knot. This is not a classical cobordism. So that's a beginning of talking about the properties of virtual cobordism, which is very interesting, and I'll continue talking about that and how the invariants that we've built so far are related to this. I won't Covanov homology next time unless I do a little bit, but then there's also the question of next time, which I'll bring up after stopping sharing. It's all right with me to meet next time, even though it's Thanksgiving week in the United States. That doesn't obstruct you, anybody, does it? Nikolai?
Sorry, Lou. What do you mean? I'm not quite understand.
Well, our Thanksgiving holiday is on Thursday. We'd be one day past it. And
Okay.
schools often close across that time, but your school isn't closed, and I have no need to stop. So I'm perfectly willing to have a lecture next week.
Okay, it will be fine.
Yeah. Okay. Yeah.
We have only one regulation that we should finish, I think, before December 20 or something like that.
Mm-hmm. Okay. So could you send me an email again with the URL for the for Nikolai's talk? I mean the
Yes,
Zoom
Lou.
the Zoom
Yes,
number for his
the
talk.
Zoom link will be different from the Zoom link for your lectures.
That's what I
So
thought.
I've
So
already
if you could send me an email with the Zoom
yes,
link. Okay.
I already sent it 1 hour ago.
Oh,
Uh,
okay. I'll look for it.
Thank you.
Otherwise, if there are there any questions? Yes, just a moment. Barry asks, can the Alexander polynomial of a slice knot be calculated from the information of the slice disk? Now, let me write a chat reply to this partly. It is a fact that the Alexander polynomial of a classical slice knot has the form f of t of 1 over t. That's a very beautiful theorem due to Fox and Milner. One of the first theorems that was proved about things like that. But in order to know that, I need to know the embedding of the knot in 3 space. It's an interesting question. Oh, excuse me, I should show that. What you would mean by information of the slice disk. If you know the way the slice disk is embedded in 4-ball, then you also know how its boundary is embedded in 3-sphere. And so in that sense, you do know enough to get the Alexander polynomial. I think you're trying to ask me, something about the saddles or the way the surface appears in 4-space. And then I don't know. I don't know how much extra information I would need. I think just knowing what saddles there are won't be enough. But there might be a way to start with a question about the saddles and the births and the deaths, and know something about what happens near them, and then deduce the Alexander polynomial without knowing more. That would be very interesting if you could do that. Other questions? Okay, then we'll adjourn for today.
Thank you.
Thank you.